Welcome back to our Riga Business School Data Structures class, and we are looking at balanced, self-balancing binary search trees, specifically AVL trees. In the second part of today's lecture, we will look at some more deletions, some more how to delete, perform a delete operation, and also how the AVL tree compares to a regular red-black trees, which are also part of self-balancing, a different type of self-balancing tree. Also, I should mention we have some materials here, also the original paper. If you're interested in, there is a link, nice site name, right, to the translation of original paper from 1962, right? Again, if you don't read Russian, if you read Russian, you can also probably find the Russian paper as well somewhere around. Again, it's been around 60 years, right? 60 years. And see, it's not very long, like 5 pages, and it talks about what we are talking about, right? How the trees are pre-influential, right? Supplied by British Library, right? And you can see how the operations are done, right? So pretty nice if you're interested in the history, right? On the actual basis, right? Okay, but let's go back to our cases. What makes it, again, slightly more complex, we can have a, let's say we have a case we want to rotate, right, 12, 20, and 15, right, you want to rotate. However, the problem is if you do the simple rotation, single rotation, well, we keep the binary search property. Unfortunately, we still don't have a valid AVL tree because our balance the world is not in balance. We sort of trade one problem for another problem. We had the right side in balance, heavier. Now we have left side heavier. So what you have to do here actually, right, in your implementation, you have to look for you need a double rotation, right? So we will need to do a double rotation, right? And this makes things more complex, of course. So you need to rotate this up first, right? And then you have this case, right? And now, of course, this is easy. Now you can rotate fine, right? And it will attach. So question is, where will it attach? 17. Well, let's see again. And it will attach here. So step 2. So 17 will attach here, right? And now we are fine, right? 2, right? 2, 2, right? This is completely fine, right? Moving up, 17 down. It might look like it's not, but this is fine. This is high 2, right? Of course, left side is completely fine already, right? So this is completely fine, and we are done. We are done with this rotation, right? So let's revisit this algorithm. Recursive search. You search for a spot, insert node, and you unwind the stack correcting heights. If you have two type of imbalance, single rotation, or if imbalance number 2, double rotation. Well, again, recursive implementations are probably easiest to implement. Iterative, you need to stack. You have, of course, some sort of stack type of data structure. You search downward for some spot, you stack the parent nodes, insert node, and then you unwind the stack manually. Again, of course, recursive function will have the same thing, stack, right? But of course, it's implicit stack. It's inside. It's built into recursion, right? So that's why we have Stack Overflow, and we have too many recursive calls, right? Here you do it by yourself. You keep track of the stack yourself. Again, remember, all recursive functions can be rewritten to be iterative. Question is vice versa. Can you make all iterative functions recursive? Well, usually it's not applicable, right? But again, you unwind the stack correcting heights, and again, same thing. So single rotate and exit, single rotate and exit again. So the cool thing is you don't really need too much rotation. It's either single rotation or double rotation, even in the hard cases, right? So that's not so bad. Right, so there's some code. This looks like C++ code to me. Void, you have pointers, right? Yeah. So on double rotation code, again, it's tricky to get it right. You can look at some examples. I won't make you do it by hand. If you had an interview, maybe I don't think it would be pretty inhuman to do this in, let's say, in a 30-minute, right? Because you would get the pointers wrong probably, right? But if you need to, of course, if you work on data structures, you will probably be able to implement it, right? But again, depend on the others to implement this usually, right? again, unless you want to challenge yourself, of course, then it would be applicable, right? So double rotation, of course, easy. Once you done the left and right, of course, these are mirror images. You need to write also a function, a member function for left, and double rotate right, and basically do 2, right? Rotate left, rotate right. All right, know the rule. Okay, now so double rotation is completed, and we are done with the double rotation. Okay. Now let's do the deletion. Easy case. Let's do easy. Let's do some deletions. We have our AVL 3. So pretty much anything here, no problem. I could do 40. Let's do 40. Right. Okay. Let's delete 40. Do we have problem? No. We just find it and delete it, right? Just like a regular binary search tree. No problem whatsoever. Right. We have no imbalances. Again, you think, okay, it's kind of bare, right? Each side, but again, remember at each level here, right? You don't have any imbalance. I mean, you have imbalance, but it's tiny, just 1, right? Off by 1, right? Okay. So, can we delete 20? Question is yes, we can delete 20, no problem. Let's delete 20. Oh, I insert delete. Sorry. I thought I insert. Oh, delete. I want delete. Delete it. Click the wrong button. Okay, so delete. So, do we have any problems? No problems, because okay, this has no children. This has 1. So there's some imbalance, right? This has nothing. This is fine completely. Over here you have imbalance, but still we can fix it, right? It's nothing to do actually yet. So we are fine. So now if I delete this, what will happen? What do you think? If I delete 30, we'll need a rotation to fix the situation, and then 50. If you delete 30, 50 will move up, 45 will move down, and 60 will be the right. So 50 will become a new parent, right? To 45. Okay, so let's see if that's if I do it correctly. Let's see. Forward. Deletion. So there's imbalance. 45. Right side is height 2. Left side is height 0. So we need to fix it. So 50 will move up. 45 will move down. 60 will stay to the right side. So single rotation, like I just said. Pretty nice, right? Pretty nice rotation. And we are done. Do we have any problems here? No, nothing broke, right? We don't need check height, right? Nothing broke. Okay. Question is now, could we break the complete right side actually? Well, if I keep deleting actually, right? Let me delete, let's say 16, 17. I'll play. So 16 also. Oh, I said 15? Okay, what did I do here? Oh, there was 16 here actually. This is actually interesting. Skip back. No, pause. Forward, right? 60 was here, right? So 60 delete. All right. So we have 15 here, and yeah, 15. We had 16 here. So that's a problem, right? 16 and 16. So let's. All right, we have some doubles here. Unfortunately, that makes things more complex. So before 15, was there any problem there? Yes, there will be a problem. Why? Let's delete 15 here. That will be more interesting. Let's delete 15. What's the problem? 15, the problem will be that this will have height 1, this will have 1, 2, 3. So let's see. Okay, now we need to fix it. So how do we fix it now? Most likely, I think 8 will move up. Let's see if I have it correct. 8 will move up. 12 will move down, and left side will be 10. Yeah. Okay, let's take a look. Yeah, so 8 moves up. So notice this here, step back, right? So 8 moves up, becomes a direct child of 16. 12, right, is more than 8. So it moves to the right side. And then 10, there's empty spot under here, so 10 attached to 12. Right, and now, do we have any problems? No, no problems. 1, 2, 3, 1, 2, 1, 2. So at no stage, everything else is fine otherwise, right? So pretty nice. Okay, and we are done. Yeah. All right. So let's see in the slides how it's done. So easy case we already covered. Let's do the hard case, right? So delete 15, right? You delete pretty easy case. So pretty easy case, yeah. So yeah, let's see. Let's delete something in middle, right? If you delete something in middle, right? Let's delete 18, right? We just take over 17, smallest one I think, or largest one will take over. That's 18, right? And it should not adjust. So if I delete 18, fine. Right, and we take the largest of the smallest, right? That's very interesting, right? So this is 17, not this 17, so that's 17 from here, and the largest from the smallest, right? It could have been largest, it could have been smallest from the largest, but okay, so we take the, here, right, if we delete 15, we take the smallest of the largest. That's another way, right? Again, depends on the implementation. Actually, either way would work. Actually, in this case, we took the highest because, of course, this had the most height. Here we had the we don't want to take so 12. We could have taken 12, but problem then we still have the imbalance. We took from the heaviest side, of course, right? So we take the, in this case, heaviest side is the right side. So if the heaviest side is the right side, we have to take the smallest of the largest, right? Right side is largest, maximum, right? All larger, so we take the smallest from the largest. Of course, if this was heavier, we would take that. If either side is equally spaced, we could technically, it wouldn't matter. You could take either side, right? So of course, you probably want to make these rules ahead of time, right? So there's some room for improvement. So deletion 12, so this will be hard case number 1. I think we already saw it, so this will be imbalanced. So we take this off. And like I said, there will be a rotation. 17 moves down, 20 will move up, then 30 will be right. Let's take a look. Yeah, rotation, right? And we are good, right? So deletion can differ from insertion, right? Because you see, rotation, the requirements can change, right? So hopefully this single rotation, we saw this already. Let's see, can we simulate another one? Let's see. Yeah, let's do this one here, right? I'll delete 14. Yeah. So if I delete 14, what will happen? Well, we'll need to find, this will have a height of 2, this will have a height of nothing, children of this 12. So we'll need to change it, and what we'll do is 11 will move up and 12 will go right, So 12 will move here, 11 will be here, and 14 of course is deleted. Let's take a look. 14. Okay, we found our 14. 14 is gone. Goodbye 14. And now 11 will move. Again, it's technically it's double rotation, right? So 11 will move up here. Here it is implemented as, like I said, 11 moves up. And yeah, and we keep this invariant property. It's almost a perfect tree, right? Complete. Right? We only had one more value and we are going to be good, right? So we could insert 20. Well, the problem is we can't. There's nothing larger, less than 17 and a half. We don't have anything we can put in here, unfortunately, right? I'd like to have complete and full and a perfect tree, but okay. All right, so do we have? Okay, let's delete. So if I delete 6, it'll be easy. Just add 7. We'll take the smallest. It'll be, I think, 4. Right? Yeah, we'll take 4. Yeah, let's delete 6. So let's delete 6. Delete 6. 6 is gone, and 4 will take space, smallest one. Again, you could have, of course, taken also 7 in this case, but the rule is as default we take the left side, largest of the left side. Okay, and we are done. That's an easy case. So if you delete 18, right? Again, probably 7 will take its place. Yeah, 7 will take its place. Let's delete 8. So, is my theory correct? So, if you delete 8, height-wise we are fine on both sides, so 7 will take its place, right? We found 8, 8 is gone. We take, find largest node in left subtree. That's 7, like I said, and 7 is gone, and we are good, we're still good. Alright. Alright, so what else? Alright, so hard to find the, okay, so if I deleted 16 here, right? what will happen? We'll take 12 will take its place, right? And everything else will be good. Yeah. Let's delete 12. I mean 16. Let's delete 16. Again, easy case, right? 12, and we are good. Fine, excellent. Right, pretty neat, and our balance is preserved. Okay, how are we doing? We're doing good. We have plenty of time. So, single rotation on deletion. Now, so hard case, right? Delete 9. So what's the issue here? Again, why not just delete? So we delete, you'll need to rotate. And like I said, rotation results will be 3 will take here and 5 will move here, right? Why? Because we need to, of course, keep the binary search property, and we can safely move this. Again, it's double rotation technically, right? Yeah, we're not finished, right? But why? So what's the problem? So that's the problem here, right? We did our rotation, say, okay, I'm gone. So why is this hard? Well, we did our double rotation, but we're not finished, unfortunately. We'll need to rebalance these two sides, right? So what will this involve? Involves moving, okay, we'll need to rotate here, 1 and 3. So we need to check this. This is like so we'll need to rotate also 1 and 3, right? Because height is, 2 here and 4 here, 1, 2, 3, 4, right? And what will happen? 17 will move up, 10 will go down, and 12 will attach to the left side. Yeah. Right. Again, so we had a deletion with propagation. So that's the hardest case, and again, that's why something doing from scratch. So we had the propagation, right? Was right. So this is what I said, right? So 10 moved down, 12 attached to the 10 again, because of course, again, why can we attach 12 safely? Because we are guaranteed everything to the right side is larger than 10, so we can safely attach 12 here. Again, it's still a binary search tree. That's the most important thing, right? If we temporarily in the process, or AVL tree is not, we have multiple steps, right? It's not atomic, right? We have multiple steps or multiple operations. We might, for a moment, or it might not be a full AVL tree, but of course, in the end of our operations, we are going to be also have AVL tree. But it's very important to keep the binary search property at all steps. And now we are any rotation. That's the invariant. That's our goal, basically, to keep the binary search property. And of course, in this process, our tree should remain well balanced. All right. And so double property, right? So deletion, recursive, search, search download node, delete node, and delete node, unwind, correcting heights as we go. You imbalance 1, single rotate. You imbalance 2, or don't care, double rotate, right? So either you have, don't care, meaning you have 2 sides, right? So you can rotate either way. Stacking parent nodes. So again, notice there's no exit here. In this is pseudo algorithms, right? So unwinding stack, we have to correct the heights, right? So that's the thing, right? So deletion is harder than insertion in AVL tree, and I think that's why AVL trees are kind of hard to implement, right? So how could we build it, right? So we just have, if it's in unordered, right, then it's just n log n, right? Because each log n it's each insertion, as we already saw in our big O cheat sheet. Where's my big O cheat sheet? Big O cheat sheet is gone. All right, log n. So if you have n elements, of course it'll be n log n. There is actually a way, I think, if it's sorted. It's not covered here. There might be a way to beat this, right? If you have sorted elements, you could insert them, I think, in n time without log n part. Right? If it's already sorted, we could just start in the middle, right, and just do, just use a regular sort of binary, split. You could do that, right? Start in the 18 and sort of like input, then you don't need any rotations, right? So insertion will be, immediately, right? That's a possibility, right? So yeah, so divide and conquer, right? Divide problem into parts, right? Solve each part recursively, right? So you did, using a divide conquer algorithm, where you could divide it in half. But I think it's still also going to be log n, right? Because you do each step. No, I guess it's all 1. I guess, right? Each step is 1. Yeah, I think it will work, right? Divide in half, right? That's root, right? And of course, because this is talking about situation when you have sorted tree, right? You don't need extra rotations, no rebalancing. You just insert, right? So build tree example. Yeah, we start 17, left side, right side, recursively build it, right? And you are done. So I think it is actually going to be without any rotations. I believe there is a way to do it actually, right? So I think it is ON. Maybe I won't make you prove it. I don't think I will make you prove it, but it is possible if you think about it, right? Well, again, but of course that's if you have a sorted tree. So wheel tree analysis, yeah, like I said, actually the analysis, if you prove it here, right, it is actually theta n, actually, right? The analysis of this insertion, right? You can prove it actually, it is actually theta n if it's sorted, approximate, right? So you can prove it actually, it is, of course, again, in general case, it's going to be n log n if it's not sorted. So, yeah, you can prove it, right? Again, I won't make you, but there is a proof that you can build this sorting. You have a sorted list of numbers, you know, array or sequence, and you can make a AVL tree, you know, binary search tree at the same time, right? Which meets these properties in n time, you know, theta n time, you know, on average, right? So let's think of some few more things about to consider. So worst case scenario is 1.4 var log n, right? Roughly. Insert, find, delete in the worst case scenario is log n. So why is it log n? Again, why? Because again, binary search tree, you keep the height, right? So the height property is actually, you know, is a log, right? Log binary, you know, if its height is 3, you have probably at most well 7 elements, right? 8 elements, right? If you have height is 1, you have most 3 elements, right? Height 2, you have most 7 elements. Height you know, height 3 at most 15 elements, right? You can prove that, right? So log on rotations. On deletion, so yeah, so in worst case scenario, you might need upper bound, right? Rotations are needed on deletion. So yeah, so what else? What other downside? So yeah, you need to maintain the balance, you know, three digits, right? -1, 0, 1, whatever you want. Of course, you could say just height, but let's do 2-bit balance. So, well, you need 3, you know, the bits are not, you know, bits are binary. You don't have ternary values, right? So, you do need 2 bits, and you have an extra, you know, 1/4 of 2 bits, you know, is not used, right? But coding complexity, right? So again, in one of the next lectures, we'll look at splay trees, a really cool structure optimized for randomized access, for frequent access, for caching, but we also red-black trees. So maybe let's talk about what's the alternative is the red-black trees. So which ones should you choose? There's discussion. It turns out, if you see, let's look at our C++ map, right? C++ map. Map C++ reference, right? If you look at here, it is sorted associative container, right? So technically, right, usually, notice this part here, usually implement as red-black trees, right? However, there's no requirement. It could technically, these could be also done as AVL trees. So which one should you use, right? Again, if you have a choice, right? Well, there's been talk about this, Stack Overflow, of course, right? Right, so the key part is AVL trees maintain a more rigid balance. I mean, it's apparent, right? With red-black trees, you have a more loose, right? You can have a less balance, but or insertions, deletions require more rotation. So again, as in everywhere else in life, there's no free lunch. You get faster lookups, but slightly slower insertion deletions as compared to red-black trees. So it really depends. If you need to do a lookups, you probably want to do AVL tree. So red-black tree, well, if you do maybe more insertions on deletions, then maybe red-black tree might be slightly better. Again, I want to reiterate that this is on a complexity scale. They're both equal. It's just that there's slightly bigger constant. So red-black trees have slightly higher constant for the excess. So AVL trees have slightly less constant factor, right? But for insertion deletion, there's slightly higher constant for search and insertion. But again, as far as for truly large sets, they were all, both red-black trees and AVL trees tend to log n. Again, so question might be, why is red-black tree more popular? Well, it's mostly because red-black tree is slightly easier to implement. And somehow AVL trees, maybe, I don't know, because they were known very well in the Western world, but it's a Soviet invention, right? So I don't know if there's a reason. It's mostly because of coding. It's not for political reasons. It's mostly for coding reasons. But so again, geeks for geeks. Sometimes they're good, sometimes they're not so good. They have pretty nice comparison, right, of AVL trees versus red-black trees. Again, I remember red-black trees have these coloring, right, bits. So you need so red-black tree only needs 1 bit. AVL you need, well, not integer. Again, you need the balance factor. So 2 bits, you need 2 bits technically. Again, so that's why you can't trust geeks for geeks completely, right? You can do 2 bits, but integer, again, memory is getting, cheap these days. So maybe you can spare an integer, or maybe, height depends how much your height. If you have height, maximum height is 256, you could use a height, or you could store -1, 0, or 1, right? So, what else? So insertion faster on red-black trees, right? So slightly slower, right? Color, there's no color, of course, that's kind of obvious, right? So faster lookups, right? So again, so that's what you have to remember. If you have lookups slightly faster, right? Slightly slower insertion and removal. So searching, well, yeah, red-black trees, so AVL trees will be better at searching, of course, slightly better. Why? Because they're more balanced, of course, right? So now what else? AVL trees are used in databases, right? Well, yeah, map, like I mentioned, map, multi-set, multi-map, right? So many things in languages. Again, I wouldn't say database, maybe yes. They also use B trees, of course, right? So there's a balance factor. There's no balance factor here, right? So again, more time for balancing because, of course, these removal insertion operations. Again, so hopefully this gives you again. The big picture of view of these two different self-balancing structures. Again, there's somebody asked a question in Stack Overflow. 2 concepts. Why do we have 2? Right, because they're different names. They're 2 different self-balancing tree structures. They're both binary search trees. They just use different methods of balancing and different definitions of what's a good balance is, right? So that's a big picture answer if you want. So what else? We covered the trees, we covered the differences, right? And I think we're almost done. Right, so you'll have to take a quiz to do on AVL trees. There is also, yeah, so implementation, right? If you really want to do this, there's nice discussion on AVL trees at there's a library called libAVL. Well, not surprisingly, even though they also do B trees. They have a really nice explanation, like what I showed you earlier in the class, right? Why we actually need them, right? So these pathological cases, right? That's why we need the balanced tree, right? And this is a C implementation. You can see how it's done. It's an open source. It has some nice reference to Knuth and Corman, CLSR, right? So you can read up on the different structures, and it compares also to B trees. So this is C, so this library you could use, this AVL library, right? AVLH, right? I think it's open, it's GPL, under GPL, right? I believe so, right? Yeah, I think so. libAVL, let's check. Yeah, GNU is not Unix, right? Pretty cool library, right? They have a binary search tree library, right? Provide pretty good documentation also. You can also try to see if you want to do it yourself. Again, try your hand. There's a Geeks for Geeks also has a reference to this. So Geeks for Geeks AVL3, right? You can look it up. See how it's implemented, right? Again, maybe not the best code, but again, alternative view to the official documentation, right? Again, let me not sign up for anything. My ad block is, I guess, off. So yeah, right, and you can see insertion, all these cases, rotations, right? And there is also C++ code if you're interested in, right? C++ 14. Actually, again, remember, this is, if you see this, this is not standard header. Remember that again, right? That's why these examples are not to be trusted completely. But you can see, of course, the node, how you define node. There's a key. In this case, it's an integer, right? Left, right, and height, right? So you store height. Again, we could have used 2 bits here, right? You know, instead of height, right? Utility for height, and we get maximum, you know, get max if you don't have it, right? Again, this is not maybe not perfect code, but it's good enough, right? And then you have, of course, nodes, right? And you will have balance, and where's the preorder, main, right? Node root. This doesn't have a, again, this works, but you probably want to have the also make an AVL class, right? This just has nodes in the main. Again, so this is code you could use and improve on, maybe adjust, right? Not something to be used as is, right? You looked at some other language examples, right? So that concludes our discussion on AVL trees. Again, usually you will see them underneath somewhere. Again, having a balanced binary search tree is quite important in many different applications. So AVL trees are one of the ways of doing it. Again, we will look at splay trees, which are next lecture, which are very, again, advanced structure for accessing data in more appropriate for, you know, caching purposes. But again, still a balanced tree. And then we'll proceed some more tree structures. Alright, so thank you everyone, and I will see you in a class next Thursday most likely.